All right, so we are going to do lesson 2 again. We'll go over some describing data. So thank you for, if you haven't already put your, hi JB, if you haven't, oh, okay, no, it's okay. Do you want me to call you JB or Jimmy or like, I mean, a lot of people actually call me AG, so, but my name's Anne-Marie Gardner, so, all right, Jimmy, what's up? Okay, welcome. So yeah, if you haven't already got, yeah, everyone put their ID, or I used to say ID and everyone put their 9-digit like Penn State ID. I was like, no, your emails, and I just try to say your email. But okay, so let's do chapter 2 again. Were you all here on Thursday? Maybe. Do you remember? Do you recall? Okay. Okay, cool. I just want to check. I always like to ask because sometimes, I don't want to drone on about stuff. If anyone's, not, if you don't want to be bored. So, but anyway, let me move my screen around because I can't see my. Okay, cool. Let's do this. All right. So, quick review of categorical and quantitative variables. This is important for this lesson because we want to make sure we understand the concept of these so that we can pick out different graphs and whatnot, depending on what types of variables we can use them for. So just to review, we have our categorical variables. These are going to be names, labels. They're going to be categories without any values attached to them. We have nominal and ordinal. Nominal just can be groups that don't have any order. Flavors. I feel like I'm always thinking about food. That's why I always use that example. Colors, that kind of thing. And then ordinal are going to be variables that have to take on some sort of order, hierarchy, class rankings. I always use that one. Or like schooling levels, that kind of thing. So yeah. And then quantitative variables are going to take on some sort of numerical value. So values from 0 or really any could be negative. That, on the number line there. Discrete are going to be, they can only take on a set number of values, such as like whole numbers. They can't be like fractions, that kind of thing. And then continuous means that they can take on any value on the number line there. It's just a quick review of that. Okay, so first we're going to talk about quantitative data displays. So these are going to be displays that you would use if you had the data that involves numbers. So you wouldn't ever put categorical data on these, so these are just things to keep in mind. And we'll do a few questions, but you want to make sure that you understand the difference for these. So a box plot and side-by-side box plots are the same thing. They're not too much different, but our box plot's going to be representation for quantitative. Oh my God, for quantitative data again. The box is going to be the middle 50%. That's what we're talking about here. And then this line is going to be our median. Oh my gosh, I've never drawn such a straight line. Proud. And then we just have like our max and our min. And we also will talk about how this is like our IQR, this 50% here. You can also draw a box plot, and I'll show you later something like this. It could be horizontal too, so it doesn't matter. Side-by-side box plots are going to be the same idea. It's the same thing as a normal box plot, except we're talking about 2 or more groups. So in this case, our group is going to be gender, so we're talking about men and women instead of maybe this one would just be men or something. So you still have one quantitative variable, so this would be age, your quantitative variable, and then but you have 2 different groups. That's the difference there. All right. Next. Oh my gosh. Okay. Another type of quantitative data display here, we have a histogram. So these are good for displaying large amount of data because you can put like a bunch of data sets within like seemingly like smaller square or like bar there. And you can also, like I said, you might see these like written horizontally. That's totally normal. You can do any of that. And this is just showing you the amount of that data. Remember that the bars touch for histograms because they're sharing a value because they're on a number line. So this one goes from 0 to probably about 50, I'd say. I'm just estimating. I would actually count these out if you want to. But so that means that, they're sharing this point here in between each bar. So that's why they're allowed to touch. So quantitative, histogram, bars touch. Advantage, like I said, they can show large amounts of data. I could make a histogram that's like, 1 million, 2 million, 3 million. And if I represent it like this, I can show this would technically represent like 1 million. And then this could represent 2 million. So that's what I'm saying about that it can represent a lot of data. And that's in comparison to a dot plot. You can't do that much data. They're better for individual observations, which is a disadvantage of histograms. So individual observations, like that would be difficult here because you have to do 2 million dots. Like, no, don't do that. So with our dot plot, we can show those individual observations, which is where that comes from. All right. So next, we are going to talk about Z-scores. So this kind of goes, along with quantitative variables. That's why I want to talk about now, especially because we were just talking about histograms and dot plots, which you can see shape easily in those. So here, all our Z-scores showing us is the distance between individual score and then the mean of the standard deviation units. So our Z-score curve is always going to have a mean of 0 and then a standard deviation of 1. So that means that our mean is going to be here, and then our standard deviation equals 1. So 1 standard deviation away from the mean is going to be 1, and then 2 would be 2, etc. I didn't really draw this well. There'd be 3 over here too, but it would kind of be represented like that. So yeah, your Z-score is basically standardizing your original data. So whatever data you have and whatever the mean standard deviation is, it's changing your original mean to the mean of 0. So you're taking, let's say, your mean and your original score is like 55, and then your standard deviation from your original score is 27. All we're doing to find the Z-score is we're transforming this into a mean of 0, and then we're transforming this into a standard deviation of 1. And then being able to do that is how we find our Z-score. So the way to do these transformations I was talking about is to with these equations. So this is finding the original score is like going backwards. So if you had the mean and the standard deviation of your Z-score, like if you had a Z-score and you want to find the original score, you would do this equation, which is just an algebraic transformation of this one on the left. But to find that Z-score, what I was saying is that this equation here is doing what I showed you here, is taking your original score, your original mean, and turning it into 0, and then your original standard deviation turning into 1. And then whatever value you had, let's say your value was 17, it's turning that into your Z-score. Sorry, I didn't mean to run those together. So that's what your value is going to be. So yeah, just that's an example. By the way, stop me at any time if you haven't been here before. Stop me at any time for any clarifying questions. Any like longer questions, I'm just waiting for the end so we can keep on cruising. But yeah, okay. So that's how we talk about Z-scores. Let's clear this drawing. All right. Okay, so shape is what I was just talking about in regards to like our histograms and dot plots. You can see shape really easily, and this is something we use with quantitative variables. So remember, so shape is just talking about what kind of trend it follows. So And we'll talk more about this, but like you'll have something skewed to the right here. Wow, my handwriting is horrific today. Or we'll have something like skewed to, well, but you're the same one. That's okay. Have something skewed to the left. And then, so that's basically, those are different shapes that you can have. And down here we have an example of having symmetrical, which is like basically like a mirror image. So that's basically how you would describe different shapes. Describe in terms of peaks. You also see this. So like this is like an example of a unimodal graph shape, and then like bimodal would be if it has like two different bumps in it, I guess. So this is another example of that. Okay, cool. So next, we have, this is just discussing what I just kind of drew an example of. So if we have a skewed distribution, this is going to be different. It's taking like a symmetrical distribution, but showing that there's like something going on. The values are more spread out on one side or another side. So if we're skewed to the right, that means that our values on the right are going to be more spread out. So as you can see here, this line here is much longer on the right. So that's saying there's much more data spread out over here. And then our Q2, our median, is going to be our, technically this is, so our median's there. And then here you have your, this is going to be your mode. The highest point in the graph is going to be your mode because that's the most frequently occurring one. That's why it's so high up. And then same thing skewed to the left. It's so spread out over here on the left. And then we have the mode would be up here on this one in that case. And here's our maximum and our minimum. Box plots are really good visual situations that you can look at. So yeah, and like also, yeah, different ways that we call it. Skewed to the right, we also call it positively skewed because these are the positive values. Wow. These are the positive values that are more spread out over here. And then skewed to the left, we also call a negative skew because they are the negative values that are more spread out. So I do not tutor in spelling, obviously. Okay, central tendency is basically a way that we can describe our distribution and the different parts of it. So we have our mean, which is basically the average. You take all your values, add them up, and divide by the total number of values you had. Median is the middle of your distribution. It's resistant to any it's resistant to movement of like addition of values, no matter what the values are. As long as they're in the same position, you can change the values of them by any number, and the median will stay the same, as long as you still have the same number of values in the same position. Mode is your most frequently occurring value, and then an outlier is just an observation that's way out of line. It's one that is not as it doesn't like fit in with your data. So your data usually follows some sort of trend, and if there's one that's way offline, that's going to be an outlier there. Okay, so these are other ways that we can describe quantitative data. So our range is showing us basically from our maximum to our minimum of, so that's like all of our data, what's the range within it. So if you have your minimum, your maximum, that's going to be all your data. And then your interquartile range is going to be the same thing. It's going to be a range, except it's the range within between Q1 and Q3. So that's the main difference here. So it's showing you the range within here, while in regards to this one, it would be showing you the range from, let me use a different color. I love colors. It would be showing you the range all the way from the minimum to the maximum. So that's the only difference in here. We're only using the interquartile range because it's within the quartile. That's why we get that number. 5-number summary So our minimum and our maximum are pretty self-explanatory. You know, our largest value and our smallest value. So the smallest value is our minimum. Largest is our maximum. They're shown by this. Another thing to keep in mind, sometimes outliers are shown by asterisks. So as one of my staff professors used to say, they called it aesthetics. So sometimes I accidentally say that just because I liked how they said it so much. But but those are different ways that you can utilize that. And then we have, and those, I mean, that's just like, you know, we'll get more into that, but that's like an example of outliers. And then in regards to your quartiles, you have Q1, you have Q2, and Q3. So remember, this middle part here is your median. Wow, that's just not good. Okay, it's our median. So remember, that's our middle part of the data. 50% of the data lies below that, and 50% lies above. Our Q1 is in the 25th percentile, and like I said, Q2 is going to be, our 50th percentile, and then Q3 is going to be our 75th percentile. So that's just saying, so remember, percentile is telling you what percent of the data lies at or below that point. So in regards to Q1, 25% of the data lies at or below Q1. 50% of the data lies at or below Q2, and then 75% of the data lies at or below Q3. And if you think about like your maximum, this is technically in the 100th percentile, which we usually don't use because it's kind of self-explanatory. That means that 100% of the data lies at or below your maximum. Same with your minimum. It's technically the 0, if that's not really a thing, but saying that nothing lies below because that's your minimum. So that's another way to understand percentages, percentiles. That used to be something that would trip me up. So yeah, okay. Standard deviation and variance, we talked a little bit about with our Z-score. So remember, our standard deviation is going to be the difference between the point that we have and then the mean. And our variance is going to be the average of all those squared deviations. So our variance is going to be like our standard deviation squared is going to be our variance. And then our variance, this is another way to write it. A lot of the things I write out are just algebraic manipulations of an equation. So these are going to mean the same thing, but it's just another way to look at it. Our variance is equal to the square root, or our variance, yeah, is equal to the square root of s. So if you were s squared. So if that's going to be it, because our variance is s squared. So then if we take our variance squared, or the square root of our variance, we're going to get s squared in this case. This one can usually be confusing to some people. So usually I try to utilize this one the most, because usually you're going to be given the standard deviation. But if you're given the variance, just take the square root of it. And that'll give you your standard deviation. So that's another way to look at it. So yeah, remember our standard deviation is our spread. That's another way we call it. It's our spread of the data. And so if we have our mean here, our standard deviation will be the average of, so if we go out one standard deviation, so this would be one standard deviation. So we're going to be like, how much is that? So we have our mean, and then this is going to be a standard deviation. So this is going to be 1, but let's say that our standard deviation was equal to 4, and we had a mean of 2. One standard deviation would be 6, because it'd be 2 plus 1 standard deviation, which would technically, I don't want to confuse you, this is going to be 4 units over, because our standard deviation is 4. So we're going to move 4 units over, so 2 plus 4 is where we get the 6. And this is still 1 standard deviation, but 1 standard deviation is worth 4 units. So if we go over 1, we add 4. If we went over 2, we would add 8, that kind of thing. So that is standard deviation, also known as spread. Spread the butter. Okay. I don't know why I said that. Okay, empirical rule. So This is something important, definitely. It's not only important just to understand, but you'll see other things that come up in the rest of the semester that will be explained by the empirical rule. Like, we won't directly relate it to that, but if you're confused about it, you can bring it back to this empirical rule and be like, oh, okay, that's why we use a multiplier of 2. That's why this and that, you know. So definitely have a good grasp on this. You'll see it often in future situations. So all it's saying is that if you have a bell-shaped distribution, so that has to mean that it's normally distributed. And then if it is normally distributed, that means that we're able to make these conclusions that 68% of our data lies within plus or minus 1 standard deviation. So that would be from here to here. That's going to be 68% of our data lies below the curve between plus or minus 1 standard deviation. So that's all of this stuff. And then at another point, plus or minus 2 standard deviations is going to be 95% of the data. So including the 60%, this is going to be 95% of our data plus or minus 2 standard deviations. So if you think about it, 60% of the data is within this blue area, 95% is within this orange area. So if you were to take 95 minus 68, let me just do that. 27. So that means that, yeah, 13.5% of, let's write this up. So technically 13.5% of the data lies within these extra parts. 13.5. Because if you think about it, we added whatever amount to 68 to make this 95% of the data. So technically we added 27%, and then if we split that equally, we're going to get the 95% and the 27 extra for the 68. So, and so on and so forth, between 3 plus or minus 3 standard deviations, we're going to have 99.7% of the data. So it's basically almost everything. So that's where we get that from. Okay. Okay, so now we're going to talk about categorical data displays. So remember, categorical data, this has to do with groups. Not really they don't have numerical values attached to them. So yeah, categorical, and we're going to first talk about one variable. So first we have a frequency table. This is just talking about, so in this case, you'll have each category of your categorical variable. So in this case, your categorical variable is campus, and then these are going to be each different variable within that, each group. And as you can see, these don't have values attached to them, you know, world campus, Commonwealth campuses, whatever. There's no value attached to them. They're just different groups. And then all it is showing the frequency of them. So how frequent do we have a student in University Park? So this is going to be like the amount. This is much higher now, actually. This is old data, but so it's just showing you the frequency. And then pie chart is a good way to represent percentages, a good visual representation of that. So yeah, you'll have different slices of it, so we can easily see that almost half of students' undergraduate enrollment comes from University Park students. If we're talking about like all the campuses, Penn State, almost half comes from University Park. We could say next is our Commonwealth campuses. And even if we didn't have these percentages, we can still look at it. Like, even if I were to make a pie chart and have something like this, you know, and like we could say these are like different colors. So we could be like red, green, blue. Even if I didn't have percentages, I can say red has the biggest percentage, green has the second biggest, blue has the smallest, you know. So that's just a different way to look at it in this case for a pie chart. So they're pretty, they're good visual situations for categorical data. Okay, another way to represent categorical data is a bar chart. Bar graph, bar chart, you also hear it, chart, it's the same thing. So this is just showing, so down here, it's the same idea. This is going to be our categorical variable. I'm really struggling with the spelling today. So that's our categorical variable, and then these are each group that we have within that. And then similar to a frequency table that's showing, it's not showing you the numbers, but showing you how frequent it is, like with a visual. So as you can see, University Park is most frequent. It has the highest bar, and then the least frequent would be PA College. Let's hit it down here. You can also see, just like histograms, you can see bar graphs represented like this. And remember that there's space in between these, because you don't really have a common connection between two categorical variables or two groups. There's not like a common tie between University Park and Commonwealth campuses, theoretically speaking. So you would never really put them touching each other, because that doesn't really make sense. So bar graph, categorical data, and then they're separated. So keep that in mind. So yeah, that's another way we can display categorical data with one variable. Okay, so now we're talking about two variables. So if you have, in this case, you can see we have, we're still talking about categorical, so they're groups, but in this case, we have two variables, which would be sport and then plus gender. So in this case, you can look at the kind of the intersection of these, like where males intersect with basketball, how many people are males, and then also like basketball, so that would be 22 in this case. All you do is just kind of, find the crosshairs of where they meet, and that'll tell you. So it's still showing you the frequency. Like in this case, you can see like how many females total do you have. That number would be down here. If we had like if they actually put total down here. So you would just add all of these together, and then that would equal your total. So you can still see the total number of each, and you can see down here, like the total number of people in football is going to be 42. So it still shows you the total, but you can also see the intersection between the two different types of categorical variables. So that's the main difference for these. Okay, and so this is just kind of like growing on the bar charts and the bar graphs, because we're talking about two variables now. The first one that I showed you would have been with one variable, so this would be if we had a graph looking like this, that would be one variable. But in this case, as you can see with these keys, we have two different variables, so they represent them by colors to change them, to show the difference. And then we have our different, so in this case, the stacked one just shows them within how stacked they are. So in this case, you'd be looking at the percentage of the purple, or the maroon one would be this percentage up here. So it looks like it's from about 50% to 100. So we could probably say this is 50%, and also this is about 50%. This looks like it's about 60, so this would be about 40%. So this is just so on and so forth, the way you can look at it. And then, so the only thing with this one, you have to, make sure you're able to break up. So this would be like 20%, break up each different part. So, and then side-by-side bar chart, same idea. It's a bar chart, but instead of stacking them on top of one another, they're just represented beside each other. So you can compare them in this way. Child visitors is smaller than, or lesser, than adult visitors in April, and also in June. But then in May, we have, higher child visitors. Higher child. So yeah, same idea as a bar chart, just with two variables there. So just kind of understand how to read those. Okay, probability. So probability is going to have to do, that's basically just the probability of an event occurring. We usually talk about them in decimals between 0 and 1. If you multiply them by 100, then you're going to be able to get percentages. The probability is very, this is just a simple equation. It's just saying the number that you have divided by your total number. Similar to an average, but you're not adding a bunch of stuff up. You're just talking about group A if you're talking about the probability of A. So like I said, it's always between 0 and 1. If you have something that's not between that, it can't be a probability. You can't have a negative probability, or you can't have anything more than 1, because you know, a probability of, let's say, a probability A is 1, that is equal to 100%. So obviously we can't go over that, because this would be if we multiply this by 100. Certain means that our probability, like if the probability is 1, it's going to be certain, and then impossible means that our probability would be 0. So there's nothing that can happen in that case. Like, that's clear. There's like there's no way that that can happen in that case. Alright, so we will go on to discuss risk and odds, which are different types of probabilities that describe the likelihood of an event happening, but we do interpret them differently. So our risk is basically the same thing as the probability. It's just saying the probability that an event will occur, so it's just the probability. So as you can see, it's a similar equation. You have your number with the outcome. So remember, like our probability of A was like the probability like of A, like with the outcome, and then divide it by total number, like your total number of tries that you could have. So risk is the same idea, and like I wrote here, you know, it's the same formula used for proportion of probabilities. And then different with odds is our denominator. So our number without the outcome is going to be our odds. So like that's how we use odds. We still have the number with the outcome as our numerator, but then our number without the outcome is going to be our denominator, and that's how it's going to show odds. So if we have risk, then you can just utilize the odds in the you can use the risk in the equation for the odds. If you're first given the risk, then you're able to do that. So, alrighty. Okay, so now we'll talk about combination of events. So remember, probabilities are talking about categorical variables. So combination of events would be the probability of 2 or more categorical variables. So we'll go through each of these briefly. So our intersection is just the probability of A and B. So that's going to be our shaded area in the middle, the probability that A and B happen at the same time. So that's an intersection. And then our probability of A and B, it's written with the upside down U. That's just a notation. So keep in mind that if you're not given, you know, the probability of A and B, make sure you understand that that notation or probability of A upside down U, B is going to be an intersection. Okay, union is kind of the opposite. It's A or B. So that's, you know, A or B happening. Make sure, you know, you understand that this has to be between 0 and 1. So if your answer is like over 1, make sure you're subtracting anything that's like not a part of A or B. It's just something to keep in mind there. So, so yeah, and our notation is going to be upside down, or not an upside down U. It's going to be an actual U looking thing. It's not a U, but it looks like a U, so that's how you can remember its union. Complements are just going to be on the probability that an event does not occur. This should make more sense with an area around it. So let's say there's this box. Our complement is going to be all this white space, which I'm now making black, but that's going to be our complement. And then, because the probability of A is going to be this blue space, it's probability of A. And then to find it, because if you think about this entire box, including the blue, is going to be probability that it's going to equal 1. So that's why if we're trying to find the complement, we would do 1 minus the probability of A. So that would be the entire box minus the blue box probability of A. That's going to give you all the area besides A. And then you can also do, if you're trying to, this is like I said, another algebraic manipulation of the same equation. We're just changing up to find our probability of A. If we're only given our complement, then you could just do 1 minus the complement. So that would be 1 minus all of this other stuff. That's not our probability of A. And that'll be able to give you the probability of A. So yeah, everything except for A. Okay. All right, conditional probability. This is where there's a condition that has to be met before we find the probability of the second one, or the probability of the first one. So our probability of that an event will occur given a second event has already occurred. So basically that second event has to occur before the first one in order to use a probability. And the way you read that, probability parenthesis A line B, like in English you would say probability of A given B. So that's just a different, this is just a different way that we use a combination of events, that they're kind of dependent on each other because the second event has to happen first before the first one does. So probability of A given B. Okay, cool. Independent events are going to be when we have two, this is still under the category of combination of events because there's two events. But in this case, they're gonna be unrelated to each other. They're not in any way like related. They don't have something in common. They don't affect one another. So like I said, conditional probability, that's not independent because they do impact one another. You have to have one happen before the other one. And then to check for independence, you can use any of those statements that I listed, 1, 2, 3, and then my laundry's done. It's just really significant. Okay. So basically, and if you find out that one of them is true, that also means that they're all true. So if you want to use whatever information you're given and whichever equation makes the most sense there. So if you're given probability of A and B, go ahead and use the first one and discuss, if that's true, then the rest of them are true. And then same thing with and if it's not true, then the rest aren't. And then, so just use dependent on what you have, whichever one makes sense. All right. Oh, we're already at review questions. Cool. Okay, so if you're here on Thursday, these are the same ones. So obviously, if you don't want to do them, I won't be offended. But it's better practice just to try them again. So review number 1. So there are 25 children in a class, 15 boys and 10 girls. What proportion of students are girls? So go ahead and try this one out and let me know what you think, and we'll go over it together. Okay, great job. So, yeah, definitely our answer is going to be C here. So you guys obviously understand it. But remember that if we're talking about our probability of something, so if you said, probability of it being a girl, we're going to take the probability that how many that we have divided by our total number. So we have 10 girls, and then we are going to divide that by our total number of students, which is 25. So then we'll get 0.4. So that's C. Good job. Proud of you guys. Okay, let's do another one. All right, so if we have 25 children and in a class, 15 boys, 10 girls, if you were to randomly select one child from this class, what are the odds that you would select a boy? So go ahead and try this one out. Okay, good. So let's go over this one. You all have very valid rationale, which is good. It means you're thinking, you're not just guessing. So remember, our odds, like the equation for that, is going to be our number with the outcome, and then number without the outcome. So if we look at this one, so we're looking at the odds that you would select a boy. So our number with the outcome is going to be the chance that you would select a boy, which would be 15. And then the odds, remember, our denominator is the number without the outcome. So that's everything, think about it as a complement, everything except for the boys. So that would be the 10 other girls. So basically everything that's not, that makes up the 25 children. So that'd be all the girls. So you would do 15 divided by 10, the number without the outcome, which would be the girls, and then you're going to get 1.5. So that's saying the odds of getting a boy is 1.5 to 1. So you have a 1.5 chance of getting a boy to every one girl. There's 1.5 boys for every girl, which doesn't make sense, but yeah. Does that make sense to everyone? Yay! Raise the roof. I just realized it was Sunday again. I'm so confused with my days. I was like, I have class tomorrow, and I'm like, no, I don't. Labor Day. Okay, cool. Just discussing the thoughts in my head. No big deal. Okay. Yeah. I understand. That's the thing. Like in statistics, you just gotta do a bunch of practice problems. That's why I usually try to put a lot into my reviews. You know, if we have time. This review is a bit longer than a lot of them. Like with me talking, I usually don't talk this much, but so yeah, the more and more you do, like looking at your notes is helpful at the beginning, but you have to do more and more because then you'll remember doing another one that was similar, and then it'll make more sense to you. So more practice problems. Because yeah, I remember in my last the last time I tutored, everyone was like, it makes sense when you do it, but like I don't know how to do it. So sooner or later, you know, and when I'm working through it, try working through it with me, you know, and then that'll kind of get it into your brain a little bit. So just a suggestion. So okay. But yeah, no, I totally understand that. Trust me, I was there. I took Stat 200. I didn't take it online. I took it in person. So I don't know what it's like online, but people have mixed. I know people have taken it both ways. There's good and bad from it. You know, you can work at your own pace online. So if you have good, you know, self-discipline, then that's good. But okay. All right. So a group of psychology students is studying the vocabulary of 3-year-olds. They take a sample of 35 children and record how many words each child says during the 15-minute session. Which of the following graphical representations should be used to present their data? So go ahead, check these ones out. See what you think. Yay, good job. So in this case, definitely, that was so dramatic. I don't know why I had to do it like that. So in this case, definitely, our answer would be B. So in this case, we're talking about how many words. So that's going to be quantitative data. So remember, if we're talking about quantitative data, we can only use either a bar graph would be for categorical, so that's no bueno. So our answers are between B and C. And remember, C is if we're talking about 2 quantitative variables, and we're not. We're only talking about 1, which is words. So C can't be the answer. So our answer is B here. All right, good job. Let's do another one. Okay. 5-number summary of the fastest ever driven speed, miles per hour, of 87 Penn State students is 55, 95, 110, 120, and 150. What percentage of students reported the fastest ever driven speed of at least 95 miles per hour? So look at this one. Let me know what you think. Yay, good job. Perfect. So our answer is going to be D here. So remember, this is our 5-number summary that they have represented here. Well, that's a big box. Okay, so if we were to write this out, this would be 55, 95 would be our Q1, 110 would be our Q2, 120, Q3, and then 150 is our max. So they say at least 95 miles per hour. So that's going to be here are 95 miles per hour and up. So this is because they're saying at least 95 miles per hour. So that means 95 and up. So remember, these are in quartiles. So this is going to be 25% of our data down here, if you remember. So that means that all this other stuff that is squiggled in is going to be 75%. That's where we get D from. So good job. You guys definitely understand this stuff. All right, a distribution has a mean of 95, a median of 87, and a mode of 80. Which of the following describes the shape of this distribution? Good answer. Okay, so our answer here, I paused my share. Oops. Okay, this can be skewed to the right. So remember, if we look at our rankings, we have that our mean is less than our, technically our mode is going to be our smallest, which is greater than our mean, or greater than our median, and then our biggest is going to be our mean. So if we look at this next slide that I have here to kind of visualize this, if our mean is our smallest, that's going to be, and this is what I was showing earlier. So if our mean is our smallest, we're going to have it skewed to the left, because if you think about it, our means are average. So if our average is to the left, that means that our value is going to be most spread out down there. And then our mode, remember, is going to be the top part of our equation here, or the top part of this graph. So because it's the most frequently occurring one, it's the highest one. And then same with this idea, our mode is going to be the little bump here. It's the highest occurring one. So yeah, that's where that comes from. So yeah, good job. It is skewed. I know, right? Then it's just like, why didn't I do that? But you'll get in the habit that it just kind of happens for you too. So, but yeah, all right, good job. Okay, find the z-score corresponding to a raw score of 109 from a normal distribution with a mean of 100 and a variance of 25. Well, okay, no, I just want to give you a chance to answer, but I totally understand. So let's go over this one. So remember our equation for a z-score is going to be z equals our original score minus our, no, you're fine, minus our mean that we're given here, and then divided by our standard deviation. Oh wait, I wrote this backwards, sorry. X minus x bar, and then standard deviation. So remember, our variance is equal to the square root of our, or is equal to the standard deviation squared. So if we want to find the standard deviation, that's equal to the square root of the variance. So in this case, to find that standard deviation, we do want to take the square root of 25, and we're going to get that our standard deviation equals 5. So remember, so we're not going to use that 25 in the denominator. We're going to use 5. So in this case, we would just take 109, our raw score, minus our mean, which would be 100, and divide that by 5. And then doing this, we're going to get 1.8 as our final answer. Yay! Does that make sense to everyone how I did that? Woohoo! Alright, cool. Let me clear this. Alright. Alright. So number 7, I think this is our last one. So at one university, 1 in 7 students who sign up for a course end up dropping or failing the course. What is the risk of a student at this university dropping or failing a course? Go ahead and check this one out. Let me know what you're thinking. No, that's good. I mix ones that make sense and then ones that are a little tricky because you obviously have to do the ones that make sense too, so you learn how to not get tripped up and assume they're going to be difficult. So definitely you're right. So remember, our risk is going to be our number with the outcome, and then divided by our total number. So, and remember, that's different from odds because our denominator is total number, not number without the outcome. So in this case, our risk is going to be 1. The students that students that sign up for the course that end up dropping or failing it, and then divided by our total number. So like 1 in 7. So out of 7 students, so we're going to end up getting 0.143. So you guys are correct. Hey, good job. Oops. Proud. All right, cool. So that's enough for tonight, I think. You guys are probably like, enough. Okay, good. So, I don't know why I did that. Okay, so yeah, like you can always watch these back on YouTube. This one and Thursdays and all of them basically. Our next review is going to be on Thursday at 10. And then if you haven't, I think everyone gave me their email, which is perfect. If you have any other last minute questions, can't wait, I know. Whoop, whoop. So yeah, if you have any questions, let me know. Other than that, we are good for tonight. You're very welcome. Good night, everyone.